All right, should be no big surprises here. First step, we're nitrating. Second step, making a sulfonic acid. Right? And the substitution is what? It's meta, because you're first putting on an electron withdrawing group in the nitro group. So the next one.
That H2SO4 fuming is second.
Sure. Not exactly. I mean, it puts on this group. You can then take it off later if you need to with dilute sulfuric acid. Okay, and this one, you didn't need to worry too much about the directing here because we know that large bulky group is going to favor the para product. But you do need to make sure that you're making the aniline and not the nitro. So to do that, you need a two-step reaction where first you're going to nitrate, and then you reduce that with some kind of metal, iron or zinc, usually hydrochloric acid. Okay. And to name that, there are a couple ways you could do it. Best way is probably para-tert-butyl aniline. That's the most succinct. Also, 4-tert-butyl aniline would be okay. And then this was probably the trickiest of the bunch. The first step, you nitrate. So let's draw that intermediate here. Okay. Now all those positions are the same, so the nitration is not directed to any particular place. Now is where it becomes important. The second step is nucleophilic aromatic substitution, right? And the nucleophilic substitution will substitute only where it can be sort of helped along by that electron withdrawing group. So it will only substitute the position ortho or para to the withdrawing group. So that means that the second intermediate is this. Now notice I didn't list a workup with water. So that means we're really kind of stuck here. Because in the strong base, that would end up being deprotonated. I mean, OH would attack and become OH, but because we're in sodium hydroxide, you would expect that to be deprotonated ultimately. What? Well, but if you put OH, it doesn't matter because we're ultimately looking at the final product, not the intermediate. Because in the intermediate now, we're going to be doing a substitution reaction to make the ether. So the final product should be this. Right, because we're doing the substitution. So that's one way to make anisols that way. The other thing that we could have done was to use something like sodium methoxide in this step. Depending on the conditions and depending on the molecule, that may or may not work. Okay. And then the synthesis. This one's a little bit tricky because it wants you to put the group ortho to this bulky tert-butyl group. So how do you have to do? What do you have to do to do that?
Acetylation.
Yes. Well. Yes and no.
Add a blocking group.
But you have to have a blocking group of some sort, right?
Yeah. So fuming H2SO4.
Right. So we want to get that blocking group on there. Now there's actually kind of a, what should we say? There can be a slight problem with this. Sulfonic acids are very strong withdrawing groups, right? And so if you are then going to alkylate or acylate, it could be a problem, right? Now it could work, so I'll give it to you. But for future reference, this can be an issue.
We can put the OH on.
Well, that you can't use that. You have to. This has to be a ketone for this to work. So we're actually going to make the ketone, and then what we have to do is actually oxidize it. And the oxidizing won't hurt this because this doesn't have the hydrogen there that can be oxidized. So actually what you could do, even better, for a better yield, is to start with the aldehyde. And end up with something like this. Now, there is a better way to do this. Actually, let's take off that group first. Yeah, I don't see why not. It may cause some problems here. I'm not sure. That's an experimental concern. What? Yeah, you need to heat that up. I guess when you put something like sodium hydroxide, you kind of assume it's in water. It's really the only way it's often used. So, but yeah. Yes, but that we know for sure you can't do in the presence of strong electron withdrawing groups, like sulfonic acid. So here's the issue here. This might not work. Okay. So how do we get around that? Although for the purposes of the quiz, I'll give it to you. How do we get around that? What else can we do? Well, we have to think about other ways to connect things over there besides directly adding carbon. So one thing you could do is you could add bromine or some other halogen. You could end up with something like that, right? Then you could reduce off. Sure, yeah. You could reduce off that group, and now you have something that you could make a Grignard reagent with. And then, of course, there are various ways that you can react this with something and then oxidize it, and so on. One that we have, I don't think we've talked about this specifically, but it actually works. You can react Grignard reagents with carbon dioxide. Remember, carbon dioxide looks like this, right? So when the Grignard adds to it, you form a carboxylate. No. So that would be kind of the quickest, most direct way. And then you protonate the carboxylate and you've got that product. For what we've seen before, you could take this Grignard and react it with an aldehyde or a ketone and then oxidize it to the acid using chromic acid or permanganate. Did you
No, it was
yeah. So I think we'll see this again when we get to the carboxylic acids chapter. Questions about that? Everybody ready for the exam on Monday?
will be.
Should be a fun one. All right. All right. So last time we went through some stuff with aldehydes and ketones, and this stuff really doesn't apply to the exam so much, but the mechanism part it certainly will. So we talked about the reactivity. We talked about the structure of these things a little bit. Why one's more reactive than the other. Steric electronic effects. Also, note that these two effects come up in aromatic reactions too. Right? We talk about steric versus electronic effects with directing abilities, with stuff like that. So Diels-Alder reactions have some steric electronic issues that we've mentioned, the endo rule, that kind of thing. We talked about the two mechanisms of carbonyl addition that we will continue to use today. And then we talked about one in specific where we form this thing called an acetal, where two equivalents of an alcohol react with the ketone or aldehyde to produce this kind of a structure. All right, and we're going to go into this in a little more detail today. So first of all, let's talk about that actual functional group. Okay, an acetal is not an ether. It is a different functional group. And this is often mistaken when we are not specifically talking about acetals, like on an exam, where you just have a bunch of random reactions. And you see something like that being made, it's easy to see that as an ether. But it's not an ether, and it can't be made using normal ether chemistry. The thing to look for is one carbon with two oxygens connected to it. If there are two oxygens connected to a single carbon, that is not an ether, that is an acetal. No matter what else is connected over here, that is an acetal at that carbon.
Will you ever see three oxygens attached to it?
Yes, 3 oxygens is called a orthoester, and we won't be talking about them much, but they exist also.
Not very significant.
What?
Not very significant.
Yeah, just, you only have time for so much stuff in a class, so I can give you some information on that another time if you really want. Okay. The other thing to note about the acetal formation, and this is where we'll start kind of working today, is that it is reversible. And we'll talk about how that makes it important for protecting group chemistry. But first, let's actually figure out that reversal. So the reverse reaction actually follows the same steps, but the arrows are different because it goes backwards. So what I want you to do is to actually figure out this backwards mechanism on your own. Part of what I want you to be able to do by the end of this class, well, not by the end, but like now, is to figure out and draw something you've done before, draw reasonable mechanisms for organic reactions. That is, can I show you a transformation and you draw a reasonable mechanism for how it occurs based on what you've seen before. So in this case, what you're going to do is take what's there and step by step move backwards to the beginning. So at the end of this reaction, we have the acetal, and we have some hydronium. And then the next step back, if you look, what we have is this. I'm just copying exactly from what was above. So how do you think we draw the arrow on that first step? What should the arrow be that shows these things transforming into these things? Yep. Disconnect. That's what we've got, right? So that's the idea. Go back step by step, draw the same thing, and although you may need to add a byproduct here or there if we were lazy about the byproducts, and see if you can draw the backwards mechanism. It follows the same sequence of intermediates, just different arrows. So whenever you're drawing a mechanism, the arrows have to tell the story. Whatever arrows you draw, the next step has to be exactly what those arrows are doing. If that's not the case, then you did something wrong. Either you're missing an arrow or you drew one in the wrong spot. The point of the arrows is to carefully account for the electrons in each step. And because of that, it's fairly easy to check yourself on mechanisms because if the arrows aren't making sense, if you find yourself having to draw something that doesn't seem like it could actually happen, then you know that's not right, and try something else. Okay. All right, now we're going to do more mechanisms now. But before we do that, let's talk a little bit more about what acetals are used for, or what they're good for. I'll just say ... See book. It actually comes later in the book. They talk about the reverse reaction later, after they've talked about all these other addition reactions. I think it makes more sense to just talk about it all together. First, we should mention the equilibrium. Acetals can be pretty hard to make because, like for this reaction, the equilibrium is actually strongly to the left. So the equilibrium constant is less than 1.
Maybe you just heat it?
No, actually, you need to... Heating can actually make it worse. You need to remove the water. So the byproduct to this is water. And so you need to actually physically remove the water using an apparatus that allows the water to escape to do this reaction. The reason for that, if we review some thermodynamics, this reaction is somewhat entropy controlled. Entropy decreases significantly going from the left to the right because you're taking 3 free molecules and you're putting them all together into one. So that significantly decreases you can call it the disorder, the entropy. Remember, delta G equals delta H minus T delta S. So if the entropy is important to the reaction, the more you increase the entropy, the more you make the more you increase the temperature, the more the entropy becomes important. So actually, the temperature isn't helping you here at all. You actually have to drive the equilibrium in another way by removing one of the products to drive the equilibrium forward. The other way you get around this, if you want to use these acetals in a way that is more practical, is to not have such a big difference in entropy. And the way you might do that is to use a diol, so you're only putting 2 molecules together instead of 1. You need 2 alcohols to form the acetal, but they needn't be in separate molecules. They can be in the same molecule. And if that's the case, you have something like this. This is known as a cyclic acetal. And that helps you out in entropy a little bit. Depending on the molecule, you may still have to use a trap, an apparatus to get the water out of there, but it's a little better. So this one goes on and off a little bit more cleanly. It's a little easier to purify off at the end. And so when we're using this in synthesis as a protecting group, these cyclic acetals are often what's used. And so now we're going to talk about what that might be. So we've seen actually reactions that we need here. But remember, the backwards reaction can be done in water and acid. And anytime you can take something on and off easily, that's a nice candidate for a protecting group. And you can use that in various ways. Whoops. So used to drawing benzene these days. let's say you have a molecule like this. And you want to reduce the ester, but you don't want to reduce the ketone. So let's say you want to do this. From everything we've learned so far, you can't. Aldehyde or ketones are much more reactive than esters. So if you were to use something like lithium aluminum hydride, you would actually reduce the ketone and leave the ester alone.
Why is it just because of reactivity?
Yeah, because of reactivity. Remember how, I don't want to jump back here if people are still writing, but we talked about ketones being more reactive than aldehydes because of the donating capability of the carbon. Well, if there's an oxygen there, there's even a much stronger donating capability because the oxygen has the lone pair. So the carbonyl carbon on an ester is much less positive than a carbonyl carbon on a ketone. Another way to remember that is if you think back to the reduction chemistry, you can use something like sodium borohydride, a more mild reductant for ketones and aldehydes, but you need a stronger reductant like lithium aluminum hydride for esters. Okay, so let's say you wanted to do this. What do? Well, you have to protect the ketone, then reduce the ester, and then deprotect the ketone to get back to where you want it. So what you do is first, we'll try a different acetal this time. First you make the acetal. These things are not reactive enough to react with esters, so they won't hurt the ester. Then you can do your reduction. Actually, let's leave it separate there for a second. And then you can work this whole thing up with aqueous acid and form the product that you want. So acetals are resistant to strong base. So they do not react with strong bases, which allows them to act as protecting groups in conditions of Grignard reagents, hydride reagents, those strongly basic environments that we've talked about. Okay. So let's look at a synthesis, or let's look at a couple syntheses where this might be an issue. All right, now on the surface, this looks like a pretty straightforward question. You deprotonate the alkyne, react with the halide, do your substitution, you're done. The complicating factor here is the ketone. A deprotonated alkyne is going to react with the ketone because any strong base will react with a ketone. Anything nucleophilic, that's what we've just been talking about, right? Any nucleophiles will react with these ketones. So if it's nucleophilic enough to do some substitution, it's going to be nucleophilic enough to react with the ketone also.
Oh, I was gonna come up with an idea.
Okay.
Could you first, could you, protonate the ketone, then put a protecting group on it, and then, add the extra ethyl group
Yes.
to the triple bond, and then, oxidize, is it oxidize or reduce to a ketone? Oxidize to a ketone? from
It's
the-
actually neither oxidation nor reduction.
Okay,
But just
I-
remove the protecting group.
Yeah,
Yeah.
remove the protecting group and then, institute the ketone.
Right, so that's exactly what we're going to do. First, you protect it.
Can we use other protecting groups? Oh, I guess that's the next step.
Yeah, there are other ways to protect things. We just talk about a couple. So then you're going to deprotonate it. And do the substitution. And then we deprotect. There are some other clever uses of acetal protecting also. Like this.
We didn't learn the mechanism for,
How do you deprotect? Is it just an acid?
Yeah.
protecting group or doing that?
That's what we just did.
Well, I mean, we did for making the acetal, but
That's what it is, yeah. Just imagine these two things connected together. It's the same.
it's the same thing.
Yeah.
And why is it written as, separate FOH? Or,
Well, Let's go through it. We'll go through it. Let me show you one more example and then we'll do it. It's a good idea. So let's say you have something like this. Actually, that's bad. Alright. Let's say you have a molecule like this and you want to do something with just this alcohol here. This one on the right. Let's say you want I don't know, what are some fun things we do with alcohols? We could oxidize them. No, let's make an ether out of it. So a propyl ether. Let's say we want to make that molecule. Okay. That's not a straightforward synthesis because you can't simply put in a base like sodium hydride or something and expect that it's going to react with this one over these two. Those are all roughly in the same place. Neither one is more sterically hindered than another. They're all basically the same. So there's not really a good way to do that. Well, what you can do is you can protect these two together because they're close enough to form a cyclic acetal. You could add something like acetone in the presence of acid. And you could perhaps, if you get the conditions right, preferentially protect these two, since they're closer to each other. So it's the same acetal, but instead of protecting a carbonyl, we're protecting two alcohols. And then you could do your ether synthesis. And then deprotect.
You know what I'm saying? No, like, it's a cyclic acetate
Yeah.
as opposed
So let's look at this mechanism. I won't do this specific one because that would be annoying to rewrite a bunch of times. So let's take this and this and this acid. And let's draw a mechanism for the formation of the acetal. So we got about 10 minutes. What do we do first?
Go very fast.
Yeah.
Okay, we can protonate the cross, whatever.
You're going to protonate the carbonyl using the acid, right?
And then,
Okay. Okay, then what?
oh, yeah, then, the bonds can move up.
Yep, so now, just like before, the alcohol attacks the carbonyl. So now I'm going to show you a little shortcut. What we would do in this case is we would deprotonate here, right? We would deprotonate this one, and then we would protonate up here. That's what the previous mechanism shows us. Let's actually draw it out, and then I'll show you the shortcut. So first we would deprotonate here with some kind of a base. What it is, I don't care. And then we protonate up there. And then the next step, the water leaves. We've seen that before. This is the same, again, the same sequence of steps as before, just a different alcohol. Oops. Okay. Now before we go on, sometimes when we write these mechanisms, we take these steps here and we just kind of write that there is a proton transfer here. And you'll see this in some books, where rather than saying, okay, I take this hydrogen off this thing and then I put it on over here, we simply acknowledge that those things are happening, but we write it in one step. The reason it's done that way is this is more close to what's actually going on. You can't show the hydrogen simply jumping from here up to here. It's not going to do that. It's not an intramolecular reaction. But if we show that that's all that's going on and we say hydrogen transfer, we're not really being disingenuous with our mechanism. We're just saying this thing comes off here, ends up there. So we may do that. And I'll show you where we use that in a little bit later. Okay, so what happens next here from where we left off? Remember, the big hint that mechanisms always give you is you know the answer. You know what it has to ultimately look like. So each step you can ask yourself, okay, is this getting me closer to what it ultimately has to look like? So what would you do now to make something?
The electrons are being go to the oxygen, the other oxygen is going to attack the carbon.
That's right. So this oxygen now attacks the carbonyl the way the second alcohol did in the previous part. So now we've got this. And then we're very close to the end here. We simply deprotonate with a base. That's it. If you go back and compare that to the previous mechanism, you'll notice that they're identical. The only difference is, they're not identical, they're same steps. The difference is only in the alcohols. Rather than having two separate alcohol molecules, you have one with an alcohol on each side. Is that clearer now? Okay. So so you should be able to do these kinds of mechanisms, and we're going to practice more with other types of additions throughout this chapter and the next chapter as well. All right, we'll stop there. Any questions?